Alright, good day everyone. So welcome back to my YouTube channel Kasadigan Vlogs. Today we will be talking about chi-square test for variance or standard deviation. So this one is a symbol for chi. Here, the symbol for chi. We will not state this one as x squared, but this is a chi. Chi could be sometimes be differentiated with x squared. But as this, if we are going to write as one, this is a chi. This is a symbol for chi, the same a format with x squared, but this is a chi. Okay, let us assume this is a chi. This is how to use the symbol for chi. And this one is chi-square test for a variance or standard deviation. Okay, again, this is a symbol. This is how chi looks like. So this one, all chi-square values are greater than or equal to 0. These are the characteristics of the chi-square distribution. The second one is the chi-square distribution is a family of curves based on degrees of freedom. Again, the number one, all values are greater than or equal to 0. Okay, greater than or equal to 0. And the chi-square distribution is a family of curves based on degrees of freedom. And the area of under each of chi-square distribution is equal to 1, and the chi-square distributions are positively skewed. So those are the properties of a chi-square or characteristic of a chi-square distribution. So next is to find the area under the chi-square distribution, use table G. So I'll be presenting you later the table G. And there are cases to be followed, two cases to be considered. First is finding the chi-square critical value for specific alpha. So the specific alpha when the hypothesis test is right-tailed, and finding the chi-square critical value for specific alpha when the hypothesis is a left-tailed, and the other one and the last one is the chi-square critical values for a specific alpha when the hypothesis is two-tailed. Okay. So these are the three cases to consider. So let us have question. Find the critical chi-square value for 15 degrees of freedom when alpha is 0.05. So the test is right-tailed test. So if we're going to graph this one, since chi-square is always positive, okay, and that is skewed to positively skewed. So that is positively skewed. Okay, that is positively skewed. Mas greater ang yang skewed here. Okay, that's a positively skewed. And if this is 0. Our alpha is 0.05 here at the point. So therefore, this is 0.95. So we need to find the critical value. So table G, using the table G to find the critical value, just look at the alpha 0.05 and the degrees of freedom, which is 15. Here, our critical value could be, that is 24.996. So this is our critical value for this chi-square value for 15 degrees of freedom when alpha is 0.05, and the test is right-tailed. The next one is we need to find the critical chi-square value for 10 degrees of freedom when alpha is 0.05 and the test is left-tailed. When the test is left-tailed, what we're going to do is the value must be subtracted from 1. So that is 1 minus the alpha, if that is the test is left-tailed. So 1 minus 0.05, the resulting one is 0.95. So the left side of the table is used because the chi-square table gives the area to the right of the critical value, and the chi-square static cannot be negative. The table set up so this gives a value for area to the right of the critical value. In this case, the 95% of the area will be to the right of the value. So if the degrees of freedom here, so what would be the degrees of freedom when that is 95 and the degrees of 10. 1095. That is our critical value for this chi-square values 3.9, okay, 40. Okay, this one is the critical value. Next, let's have this one. Find the critical chi-square values for 22 degrees of freedom when alpha is 0.05, and this is a two-tailed test is conducted. So, since this is a two-tailed test, if we're going to graph this, okay, always, if the two-tailed test, we have to get the alpha divided by 2, that is 0.05 divided by 2, that is equal to 0.025. And this one is our 0.025 and also 0.025. To get for the critical value in a right tail test or right part of the larger value, we just have to look at the value here in this case. In this case, our alpha, we have 0.025 with a critical degrees of freedom of 22. So we have to locate here. So 0.025 and 22. This one, 36,781. So this one is our critical value is 36,781 for this right portion. And the left portion would be, okay, 0.025. So 1 minus alpha divided by 2, that is 1 minus 0.025. So what is our 1 minus 0.025? That's 0.975. So the two critical values for the left tail to the smaller area is 975 and 22 degrees of freedom, that is 10.982. Okay, these are the critical values that we need to get his in this particular problem. Okay, so note after the degrees of freedom reach 30, the table G gives only for multiple of 10 to 40, 60, etc. When the exact degrees of freedom sought are not specified in the table, the closest smaller value should be used. So after 30, so this one by 10 interval na siya. Okay. So the formula for chi-square test for a single variance is chi-square is equal to n minus 1 times the standard deviation of standard, no, the sample variance other over the population variance, that is s squared, the population variance, with the degrees of freedom equal to n minus 1, where n is the sample size, s squared or the sample variance, and sigma squared is equal to population variance. The assumption for the chi-square test for a single variance, first is that the sample must be randomly selected from a population. So randomly selected from a population, the population must be normally distributed for the variable under study, and the observation must be independent of one another. So those are the assumptions for the chi-square test. So let's proceed with problem solving. Here, why is it important to test the variance? There are several reasons. First, that in any situation where consistency is required, such as manufacturing, you would like to have the smallest variation possible in the products. For example, when bolts are manufactured, the variation in diameters due to the process must be kept to the minimum, or else the nuts will not fit from them properly. In education, we have here consistency is required in the test. That is, if the same students take the same test several times, they should get approximately the same grades. And the variance of each of the students' grades should be small. On the other hand, if the test is to be used to judge learning, the overall standard deviation of all grades should be large so that you can differentiate those who have learned the subject and for those who have not learned the subject or the subject matter. So those are the things that we need to know the importance of to test the variance. First in education, that is consistency. So let us have question number 1. The standard deviation for math SAT test is 100. The variance is 10,000. An instructor wishes to see if the variance of 20 randomly selected students in our school is less than 10,000. The variance of 23 test scores is 7225. Is there enough evidence to support claim that the variance of the students in her school is less than 10,000 at alpha 0.05? Assume that the scores are normally distributed. So here, the first step is we need to state the hypothesis and identify the claim. So HO, so we have to use this sigma squared is equal to 10,000. And H1 sigma squared is lesser than because the claim is less than 10,000. So this is our claim. Next step is we need to find the critical value. Since the test is left-tailed, so an alpha is use 1 minus alpha. This is 1 minus 0.05. So that is 0.95. So the degrees of freedom here is equal to 23 minus 1 is 22 because our n is 23. So if that is 0.95 and the degrees of freedom is 22, so therefore the critical value is equal to 12.338. That would be our critical value. Next, step number 3 is we need to find or to compute the test value. So the test value is chi-squared is equal to n minus 1 sample variance over the population variance. So there's 23 minus 1 times the sample variance here is 7225. The variance of the test score 23 is 7225 over the population variance is 10,000. Then you're going to plug in that one in your calculator. It would result to 15.895. So this is our chi-square test value. So step number 4 is that we have to compare it using graph. So since our chi-square value is positively skewed, if this one would be our critical value, 12.338, and our chi-square value is 15.895. So we have what is our decision. Since 15.985 falls in the non-critical region, so the decision is do not reject the null hypothesis. So do not reject the null hypothesis. It does not fall to the critical region. Since our claim is H1 and we do not reject the null hypothesis, the statement should start with there is not enough evidence to support the claim that the variation of the test scores is less than the population variance. Okay, so that's it. So there's not enough evidence to support the claim that the variation of the students' test score is less than the population variance. Okay, let's proceed with problem number. The next problem. A hospital administrator believes that the standard deviation of the number of people using outpatient surgery per day is greater than 8. A random sample of 15 days is selected. The data are shown. The data are shown here. This one. At alpha 0.10, is there enough evidence to support the administrator claim? Assume that the variable is normally distributed. Okay. Since the data here is in raw data, we have to compute the population and standard deviation. So we had already uh, the the video on how to compute using the standard population and sample standard variance. So I'll just have to state what is the result of the calculator. So next we have here hypothesis. So what is our hypothesis here? Our HO is, since the question is, okay, we believe that the standard deviation, so therefore our HO is standard deviation is 8. So we are using standard deviation. And our H1 is using per is greater than 8. So our standard is greater than 8. So this is our claim. Okay. So standard deviation. So the claim is all about standard deviation. So next step is we need to find the critical value. So at alpha 0.10, so that's greater. So we'll make use of this alpha. And our DF is 15 minus 1, that is equal to 14. So 0.10 and 15. That is 30.57, 14 rather, 29.1. Our CV is equal to 29.141. 5.10 rather, 0.10, 14, 21.064. That is 21.064. That's 21.064. And step number 3. So we have to compute the test value. So if we're going to make use of calculator and you're going to solve it one, so our sample standard deviation here is S is equal to 11.2. So compute it one using your calculator. And if we're going to compute the test value, chi-square is equal to n minus 1 s squared over the population variance. So 15 minus 1, which is 11.2 squared, because we have to square this based on the formula. And the given is 8, greater than the 8 standard deviation. So therefore, we have 8 squared, that is 64. So using the calculator, and you have to plug in, so we have 27.44. Then step number 4, we have to make a decision. Okay. Using graph, we could easily make a decision. That is, our critical value is 21.064. This is a right tilt test. And it falls in this one, 27.44. And this part is what is this part here, padong ana, This is our 0.10. This is the 0.10. Going here, here is that is 0.10. That is the given alpha point 10. Since that is 0.27 27.44 falls in the critical region, so the decision is we have to reject the HO since the test value of 27.44 is greater than the critical value 21.064, and it falls in the critical region. So therefore, in step number 5, if that is our claim is our alternative hypothesis, we will start and we reject the HO. So we will start with the statement there is enough evidence to support the claim that the standard deviation is greater than 8. Okay, it's greater than 8. The standard deviation is greater than 8. So next question. Okay, the next question. So a cigarette manufacturer wishes to test the claim that the variance of the nicotine content of cigarettes is 0.644. Nicotine content is measured in milligrams and assume that it's normally distributed. A random of 20 cigarettes has a standard deviation is 1 milligram at alpha 0.05. Is there enough evidence to reject the manufacturer's claim? So step 1, we have to state our null hypothesis. We have to test the variance. So variance is equal to 0.644. And stated here, this would be our claim. And our H1, so our H1 is variance is not equal to 0.644. Step number 2 is find the critical value. Since this is a two-tailed, the right-tailed is alpha divided by 2. Alpha divided by 2 is 0.05 over 2, that is 0.025. And for the left-tailed, the 1 minus alpha divided by 2, that is 1 minus 0.025, that is equal to 0.975. So these are the critical values that we need to have. And our degrees of freedom, that is 20. So 20 minus 1, that is equal to 19. So we have here our critical regions. By using this one, what would be our, our critical value in the right portion? 0.025 and 19. That is 32.852. 32.852, and the other one is 0.975 and 19. 8.907. So these are the critical values that we found in after dividing alpha and divided by 2 and subtracting from it 1 minus the alpha. So next, we have to compute the test value. How to compute the test value? We have chi-square is equal to n minus 1 squared. So what is our n? 20 minus 1. What is our variance? The variance here is 1 milligram. So 1 squared over, and the variance for the content or population is 0.644. If you're going to plug in using your calculator, it would result to 29.5. Okay, since the standard deviation here, the random sample is given 1 milligram, so we have to square. They have to square here like this. We have to square. Because the given is 1 milligram, and this is the just standard deviation. We have to square. So next step number 4, make the decision. So by graphing, this is for 0.025. For the left one is 8.907, and for the right one is 30 32.852. And the resulting one of the chi-square is here, 29.5. It does not fall to the critical region, so therefore do not reject the HO, since the test value falls between the critical values. So that is 8.907. That is 21. It falls between here, 852. It falls between the critical values because this is total test, and in the non-critical region. Okay, so this between these two critical values, it falls between two critical values, so we have not to reject the null hypothesis. And step number 5, when we do not reject the null hypothesis and our claim is our HO, we will start with the statement there is not enough evidence to reject the manufacturer's claim that the variance of the nicotine content of the cigarettes is equal to 0.644. Okay, so that's all about this problem about nicotine contents of cigarettes. Let's proceed with the p-value method. So how to compute using the p-value method? So find the p-value when the chi-squared is equal to 19.274 and n is equal to 8, and the test is right here. Okay, to get the p-value, look across the row with the df is equal to 7. So since our n is given 8, so our df is 8 minus 1 is equal to 7. And our chi-square is 19.274. So in table G, we have to find the values for 19.274. 19.274 19.274. Okay, this one. It falls between 19.274. It falls between here, this part. So 0.01 and 0.05. They are 0.01 and 0.005. So it falls between 0.01 and 0.005. So therefore, the p-value is greater than 0.005 but lesser than 0.01. So that is would be our great p-value. But if we're going to use your calculator, it would be approximately that is 0.007. But we need to have this p-value since we are using table. The p-value is between p was greater than 0.05 and lesser than 0.01 if you are using table. Okay, so next we have here, find the p-value x squared is equal to 3.823 and n is equal to 13 and the test is left tail. Okay, so we have here x squared df is equal to 13 minus 1 and our chi-square is 3.823. So left tail. So if that is a left tail, so 1 minus, okay, to get the p-value, look across the df, which is equal to 12, and find the two values that is between fold. So we have here uh, 3.823, 3.823, 3 point, okay, 571. Here, 3.823, there falls between here, 3.571 and 4.04. So it falls between 5.01 and 4.04. So they are, the value here is 0.99 and 0.975. So 0.99, so we have to get the test is left tail. So when x squared test value falls on the left side, each value must be subtracted from 1 to get the interval of the p-value. So since that is 0.099, that is left tailed, so we have to subtract it by 1 minus 0.99, that is equal to 0.01. And the other one of the critical is p-value is between 0.975, that is equal to 0.025. So therefore, we could say that the p-value is greater than 0.01 but lesser than 0.025 here. So 1 minus 0.99 and the other one is 0.974, 4.04. So the p-values is between. So the p is greater than 0.01 but lesser than 0.025. That's how to get the p-value. When the chi-square is two-tailed, both interval must be doubled. If the two-tailed test were being used, then the interval would be doubled. If that is a two-tailed test, we have to double this one and double this one. So the resulting, if that is a two-tailed test, that is 0.02 is greater this one. If that is, we have to double when there is two-tailed test. Okay, if that is a two-tailed test, the interval would be double. So let's have question. A researcher knows that the past studies that the standard deviation of the time it takes to inspect a car is 16.8 minutes. A random sample of 24 cars is selected and inspected. The standard deviation is 12.5 minutes. At alpha 0.05, can it be concluded that the standard deviation has changed? use the p-value. Assume that the variable is normally distributed. So the first step that we're going to have is, again, we have to identify our hypothesis. Since we're talking about here the standard deviation, our standard deviation is equal to 16.8, and our H1 is, the standard deviation is not equal to 16.8. So since the researcher noted that the standard deviation time it takes to inspect is 16.8. So what would be our claim? A random sample selected and inspected, the standard 12.5. At alpha can be concluded the standard deviation has changed. So our claim is the standard deviation has changed, so therefore this is our claim, has changed. So this is the alternative would be our claim. And step number 2, to compute for the standard deviation, we have first compute, when using the p-value method, we have to compute first the chi-square value. The chi-square value is n minus 1 squared over sigma squared is equal to, that is 24 point minus 1, and this is the given is 12.5, so therefore we have to square, and the standard deviation given per the population we have to square. Okay, so if we're going to plug in, the resulting would be 12.733. Step number 3, we have to locate in the closest value for this 12.733. The closest values here, false. Okay, 12.33, that is 12.33. They're here. 12.33 is, and the degrees of freedom of 23. Okay, this one. Our DF here is 23, and closest to those one is 11.689 here. 11.689 and 13.091. So this is between 0.975 and 0.95. Since the values are found to the left of the distribution, each value must be subtracted. So 1 minus 0.975 is equal to 0.025, and the other one is 1 minus 0.95, that is 0.05. So since the two-tailed test, the area must be doubled the p-value of the interval. So we have to double this one. So our p-value is double this one. We have times 2. So one times 2, we have 0.05. And the other one is 0.10. Okay, that is the p-value is between 0.05 and 0.10. And step number 4. Okay, step number 4. This is the upper and the lower value here, and since this is lower, doubled. If that is two-tailed test, we have to double this one. And since the alpha is 0.05, the p-value is between 0.05 and 0.10. The decision is, so the p-value is not to reject since the p-value is greater than alpha. Okay, since the p-value, our alpha is 0.05, and since between 0.5 and 0.10, the decision is not to reject the null hypothesis since the p value is greater than the alpha. If that is a p-value is greater or equal to the alpha, so do not reject the null hypothesis. And summarize the results. Step number 5, there is not enough evidence to support the claim that the standard deviation of the time it takes to inspect the car has changed. Okay, so in this case, we have not to reject the null hypothesis because the alpha is 0.05 and that is the alpha is greater than 0.05. So that is p-value is greater than if the p-value. So what is our p-value? Our p-value is here between 0.05 and 0.10. If the p-value is greater than the alpha, this one, 0.05, this is greater because that's between 0.10 and zero point 0.5. So we have not to reject the null hypothesis. There is enough evidence to support the claim. Okay, that's the first statement if we're going to state the summarize the result. If you're going to summarize the result. Okay, try this at home. We have here 4 problems to be submitted during our class. During our class. So I'll just give you the time to answer this, try this. Thank you so much. And you have to submit that one before our time.